How sure are you that this moment, right now, is uniquely real and everything else is either gone or not yet here? Because the physics you use every day without knowing it says that picture is false in a deep, uncomfortable way. But before we continue, please subscribe to the channel to give your support. Let's continue. Start with something very simple. You feel like there is one shared now across the whole universe. You think that as you watch this, there is a definite thing that is happening right now on the Moon, on Mars, and in the Andromeda Galaxy, about 2.5 million light years away, roughly 1.5 times 10 to the 19 miles, around 2.4 times 10 to the 19 kilometers. One giant synchronized moment. That sounds obvious. Relativity says it is wrong. Here's the key idea. Take you sitting still on Earth. Take another person moving past you at a few thousand miles per hour, a few thousand kilometers per hour, maybe in a fast spaceship. You both look at some distant place in space. You both try to answer the question, which events out there are happening at the same time as the reading on my watch right now? When you use the real equations of special relativity, your answer and their answer do not match. You slice space-time differently. You and the other person disagree on which distant events belong in the present. This is not about delays in signals or slow communication or bad equipment. You can correct for all that. Even after correcting, the theory says, and experiments confirm, that there is no single cosmic time that everyone must agree on. There is no universal master clock. There is only now inside your own state of motion. So the first blow is simple and brutal. The thing you treat as most obvious, a global present moment, does not exist in the laws of physics. If there is no universal now, something even more radical follows. What you call past, present, and future cannot be three different states of a changing universe. They have to be something like three different regions of one fixed structure. That is the dangerous idea. Time does not flow. The future is not being created. The whole history already sits there in space-time. So why did physics have to go this far and not just tweak a few numbers and keep the old idea of time? Relativity is built around two very stubborn facts. First, the laws of physics look the same in every frame that moves at constant speed in a straight line. If you are floating in deep space inside a smooth ship with no windows and you turn off the engines so you coast, you cannot tell if you are really moving or really at rest. Your lab experiments give the same answers. Second, the speed of light in a vacuum is always the same, about 186,000 miles per second, 300,000 kilometers per second, no matter how fast you are moving when you measure it. In ordinary pre-relativity thinking, speeds just add. If your car goes 60 miles per hour, about 100 kilometers per hour, and you throw a ball forward at 60 miles per hour, someone standing on the road should see the ball at 120 miles per hour, about 200 kilometers per hour. That works great for balls. If light worked the same way, then chasing it should make it look slower, and moving toward it should make it look faster. But when people actually measure light speed in different directions and at different speeds, they keep getting the same number back. To protect those two facts, something has to give. You can either break the idea that the laws of physics are the same in all non-accelerating frames, or you can break the idea of universal time. Nature clearly keeps the first fact, so you are forced to let space and time bend together. Distances shrink, time stretches, and simultaneous stops being absolute. Once that happens, the picture of the universe as a 3D world constantly updating in a separate time breaks. The clean picture is a four-dimensional block of space-time that just is. That still sounds abstract, so where did this really start to crack open? Which experiment first said, your background picture of time is wrong? One of the big turning points was the Michelson-Morley experiment in 1887. At that time, physicists thought light had to move through some invisible medium called the ether, the same way sound moves through air. Earth orbits the sun at about 19 miles per second, 30 kilometers per second, so we should be moving through this ether wind. If that is true, then light moving along the wind and light moving across it should take slightly different times. Michelson and Morley built a device with two perpendicular arms, each about 36 feet long, around 11 meters. A beam of light entered, split into two, ran down both arms, bounced off mirrors, and came back together. If one arm's light took a bit longer, the waves would shift against each other. You would see bright and dark bands move when you rotate the device. As Earth turned and moved along its orbit, there should have been a clear pattern. They saw no such pattern, no consistent shift, no sign of motion through an ether. That null result was not boring. It was a loud message. Light's behavior is not being measured against a physical background like air. Its speed is treated as built into space and time. That experiment helped kill the idea of absolute time and absolute rest. Once the ether was gone, the only way forward was to rewrite what space and time are. So now you have a new picture. Space and time form one structure, spacetime. There is no absolute rest, no absolute now, and light's speed is a fixed part of the geometry. Where do you, the person watching this, fit inside that? In this space-time view, you are not a little 3D shape sliding along a separate time axis. You are a four-dimensional curve called a world line. Take some key events in your life: the point where you were born, the point where you started school, the point where you pressed play on this video, the point where you will do something 10 years from now. Each one is an event in spacetime, with 3 space coordinates and 1 time coordinate. Join all those events and you get your world line. From the outside, in the equations, that whole line is one object. The part you call past is the earlier segment of the line. The part you call future is the later segment. The math doesn't mark one end as more real than the other. It just says this is the path. The feeling of moving along it is your perspective from inside the line, not something the universe is doing to the line. This can sound like a word game, so the obvious challenge is this just interpretation, or does the block picture actually matter for real, hard predictions? The answer shows up in technology you rely on. Global positioning, GPS, only works because the timing of satellites and ground receivers is calculated in this space-time language. Particle beams and accelerators are guided and focused using these same relativistic rules. Cosmology codes that match data from billions of light years away treat spacetime as a whole structure, not as a system ticking from one frame to the next. The block interpretation is not a decoration. It's the simplest way to understand a theory that works with extreme accuracy at nanosecond timing and micrometer distances. So the dangerous idea is this: physics describes you and everything else as four-dimensional tracks inside a fixed spacetime. There is no global now sweeping forward. Past and future are just different sections of the same object. Time does not flow, it is laid out. That raises the next problem, and it's even more uncomfortable. If the universe is this fixed block, if your entire world line is already part of the structure, then what does space-time itself look like, and how can you make sense of a future that is already there without feeling like everything is pointless? How do you describe a universe where nothing is literally created from moment to moment, but you still see things move, change, live, and die? That sounds impossible, but this is exactly the kind of picture physics was pushed into when it turned time into geometry. So what does it actually mean to turn time into geometry? About 3 years after Einstein wrote down special relativity, his old math teacher, Hermann Minkowski, went one step further. He said, stop thinking in terms of 3 axes for space and 1 separate axis for time. Treat them as one 4-dimensional structure, spacetime. In this picture, every event gets 4 numbers, 3 for where it happens, 1 for when it happens. The key object here is something called the space-time interval. It's a specific combination of how far apart in space and how far apart in time, after you convert the time gap into a distance with the speed of light, about 186,000 miles per second, 300,000 kilometers per second. Different observers moving at different speeds will disagree on distances and on time gaps, but they will all agree on this interval. That number is the same for everyone. That's what counts as really the separation between two events. That is a very hard claim. You can change your speed, switch rockets, pick any straight line motion you want, and the laws of physics insist that when you compute the space-time interval, you get the same answer as anyone else. So instead of treating space distances and time intervals as basic, you treat the interval as basic, and you see space and time as different ways of slicing up the same four-dimensional gap. This is where the block idea starts to become unavoidable. If everyone has to agree on that one geometric measure, then the thing they're measuring, the four-dimensional space-time, has to be there as one object, not built slice by slice as the universe updates. If space-time is one geometric object, then your own time should be something geometric inside it. So what exactly is the time you personally feel in this picture? Here, relativity uses the idea of proper time. Proper time is basically the length of your world line between two events, measured with the space-time geometry. Not length in ordinary space, but the amount of personal time your clock accumulates along that path. You can see this in a very direct way with muons, short-lived particles created high in Earth's atmosphere by cosmic rays. If a muon sits still in the lab, it survives about 2.2 millionths of a second. Even if it moved at normal airplane speeds, it would only get about 2,200 feet, around 660 meters, before decaying. In reality, we detect huge numbers of these things at the ground after they've traveled tens of miles, tens of kilometers. From your frame on Earth, their internal clocks are running slow because they're moving so fast, so more of them make it down before they hit their own proper time limit. That sounds like a trick of perspective, so the obvious question is, are these stretched times just some weird special case in the upper atmosphere, or is space-time geometry running the show everywhere we look? The most controlled tests happen in particle accelerators. At CERN's Large Hadron Collider, protons run around a circular tunnel about 17 miles long, around 27 kilometers, at speeds so close to light that their internal processes slow down by factors of thousands relative to clocks in the control room. These protons are guided by magnets to hit each other inside detectors with insane precision. Engineers and physicists compute exactly how their proper time compares to lab time using the same space-time geometry Minkowski wrote down. If they got that geometry wrong by even a tiny amount, the beams would not line up, the collisions would not happen where detectors expect them, and the data would not match the theory. Instead, everything lines up. Nature behaves as if space-time really is this four-dimensional arena with fixed rules. So if geometry is doing all the work, where does ordinary motion fit in? Are things actually moving, or are we just comparing different cuts of this block? In the space-time view, motion is not an extra ingredient. It's just a different way of slicing the block. An object that is at rest in some frame has a straight world line, pointing mostly along the time direction. Speeding up or slowing down bends that world line. You are not watching objects travel through an external time dimension the way cars drive down a road. You and the objects are all world lines already traced in space-time, and what you call something moving is you comparing one slice you call now to another slightly later slice along your own world line. Change your state of motion, and you literally change which set of events you group together and call simultaneous. That raises a more personal point that is easy to skate past. If motion and change are about how you cut the block, what does that say about you as a physical object? In this framework, you are extended in time the same way a rod is extended in space. If you could take an outside view of space-time, which you can't, but the math can, you would see your entire life laid out along your world line. Infant you, kid you, teen you, older you. All those stages are different segments of one geometric object. Physics does not mark the today segment with a special tag. It does not treat the future segment as a ghost that needs to be activated later. The future part of your world line is just as much a part of the space-time structure as the part you remember. That is the unsettling punchline of turning time into geometry. Minkowski's move converted Einstein's strange new rules into a clean four-dimensional picture, and experiments with particles, clocks, and beams keep confirming it. The most straightforward way to read that picture is simple and severe. Space-time is a fixed four-dimensional arena. Your life is a path inside it, and the difference between past and future is not that one exists and the other doesn't, but just where you are along that path. But if all of space-time is sitting there at once, and your now is just one cut through it, then how can two people both using perfect clocks and perfect rulers both be right about events happening at the same time while completely disagreeing about which events those are? This is not a trick puzzle. This is normal behavior in relativity, and it is the reason your idea of a shared global now does not survive contact with physics. Take a straight railroad track, about 1,000 feet long, around 300 meters. Two lightning bolts hit the two ends of the track. Call them left and right. There's a person standing exactly in the middle of the track, not moving with respect to it. Light from left and light from right travel toward the center at the same speed. Because the person in the middle is the same distance from both ends, the two flashes reach their eyes at the moment same. So they say, without hesitation, those strikes were simultaneous. Now change one thing. Put you on a train moving along that same track at about 60 miles per hour, around 100 kilometers. You are still at the midpoint when the lightning hits, but now you're moving toward the right end and away from the left end. Light from both strikes still moves at the same speed, but you're heading toward one flash and running away from the other. So in your frame, you meet the light from the right strike sooner and the light from the left strike later. You see the right flash first. Your honest conclusion is the right strike happened before the left strike. So which is correct? Did the lightning bolts actually happen at the same time, or did one happen first? The detailed relativity calculation says something that feels very uncomfortable at first. Both conclusions are correct, but they are correct in different frames of reference. The interval between the strikes and each observer and the way their time and space coordinates line up allows the order of now slices to differ. You on the train are not making a mistake. The person on the ground is not making a mistake. The structure of space-time allows both sets of events to be lined up as simultaneous in one frame and not in another. This creates a problem for the everyday picture of time. If you want to hold on to the idea that only one list of events is really now at the same moment, now you have multiple lists that clash. Do you give one observer a privileged status and say, their version is reality, everyone else is wrong? Or do you accept that simultaneity is not absolute? Relativity chooses the second option. There is no way to define a single slicing of the universe into this is now everywhere that all observers must respect. If you try to pick one preferred frame, one hidden cosmic rest frame that defines the true present, you immediately break the core symmetry of relativity, which says the laws of physics should look the same in any frame moving at constant speed. That symmetry has been checked in particle experiments, in atomic clocks, in high-energy collisions over and over. No experiment has ever revealed a hidden, real present frame that the equations secretly favor. So the universe keeps the symmetry and throws away the universal now. Present becomes local. It is defined along your world line, using the way your frame slices space-time. Someone moving differently will cut space-time at a slightly different angle, and their present is a different set of events. Both cuts are allowed. There is no global referee that steps in and says, only this one is real. You could treat this as just a weird story about trains and lightning, but you are already using systems that depend on this relativity of time being real, not optional. One of the cleanest examples is GPS, the navigation system your phone uses. GPS satellites orbit Earth at an altitude of about 12,400 miles, around 20,000 kilometers, moving at around 8,700 miles per hour, about 14,000 kilometers per hour. Each satellite carries very precise atomic clocks. Those clocks do not tick at exactly the same rate as identical clocks sitting on Earth's surface. Two effects are in play at once. Because the satellites are moving fast, special relativity says their time should run a bit slow compared to clocks on the ground. Because they are higher up in a weaker gravitational field, general relativity says their time should run a bit fast compared to clocks deeper in Earth's gravity well. When you add these effects properly, the net difference is on the order of a few dozen billionths of a second per day. That sounds tiny, but GPS works by comparing the timestamps in the signals from multiple satellites and using the travel time of those signals to compute your position. Light moves about 1 foot in a billionth of a second, about 0.3 meters in a nanosecond. So errors of a few dozen billionths of a second quickly grow into position errors of many feet, then many yards, then miles or kilometers if you let them build up. If engineers pretended time was absolute and refused to correct for the frame-dependent ticking of those satellite clocks, your GPS location would drift by miles every day, and the system would collapse. The only reason it works is because time is treated as something that depends on motion and gravity, not as a universal background. Once you accept that, the lightning story stops looking like a paradox and starts looking like a simple fact about how space-time works. In a block universe view, all the relevant events already exist. The 2 lightning strikes, the person on the track, you on the train, the arrival of the flashes at each set of eyes, every tick of every clock on Earth and in orbit. Each observer's now is just one 3-dimensional cut through that 4-dimensional set of events. Different observers cut it differently, depending on their motion. Their disagreement about simultaneity is not a glitch. It is built into the geometry. The block does not update or resolve anything. It just has different valid slices. That leads to one more step that really hurts the intuition. You might think, fine, maybe simultaneity is relative, but surely the order of events is still set in stone. First, this happens, then that happens, period. Relativity says, not always. For events that can influence each other, the order is fixed. If you turn on a flashlight and later you see the spot hit the wall, every observer agrees that the button press comes before the light reaching the wall. The signal travels at or below the speed of light. The cause sits inside the past light cone of the effect. Relativity doesn't mess with that. It keeps causal order safe where signals can actually go. But consider 2 events that are so far apart and so arranged in time that no signal moving at or below light speed could ever go from one to the other. For example, a flare on a star a billion light years away and you finishing this sentence. In space-time terms, these events are space-like separated. No matter what you do, you cannot send a message fast enough from your screen to that star, or from that star to you, that links those 2 specific moments. For that kind of pair, different observers moving in different ways can legitimately disagree about which event happened first. One observer can say the flare came first. Another can say you finishing the sentence came first. A third can say they were simultaneous. All of them are valid frames. The laws of physics don't pick a winner because there's no possible cause and effect link between the 2 events anyway. The only ordering that matters, the only ordering the universe really cares about, is the one inside light cones, where causes can reach effects. So you end up with a sharp picture. Now is local, defined along each world line. Simultaneity is not a universal fact, it's a frame-dependent choice. Event order is only absolute when there is a possible causal link. Outside that, it can flip. And yet, technology built on these rules, like GPS, works with brutal precision. That leaves a harder question hanging in front of you. If even basic things like what is happening right now and what comes first depend on how you move, and if clocks at different speeds and heights refuse to agree, how far does this warping of time go when we push it with extreme experiments? And what does that do to your idea of a single shared future? How can 2 clocks that start perfectly synchronized, built from the same atoms, sitting in the same lab, end up disagreeing just because you moved one of them around the planet or raised it by 3 feet? If time were one universal flow, locking everything in step, this should not happen. But when you push clocks hard enough, they refuse to tick together, and they do it exactly the way space-time geometry predicts. Start with a classic test. In 1971, physicists took super-precise atomic clocks, the kind that count the vibrations of atoms and lose less than a second in millions of years, and put them on commercial airliners. One set of flights went eastward around Earth, one went westward, cruising at roughly 560 miles per hour, about 900 kilometers per hour, at an altitude around 33,000 feet, or about 10,000 kilometers. Matching clocks stayed behind in a lab as a reference. They flew these clocks around the world, brought them back, and compared all the readings. If time were absolute, if every second was the same everywhere, those clocks should still match the lab clocks within their small measurement errors. They did not. The airborne clocks had gained or lost tens of billions of a second, tiny amounts but well above the noise, and they matched the detailed predictions of relativity once you account for both their speed and their altitude. The eastward and westward flights even shifted in opposite directions, just as the theory says. That result is not a cute effect for documentaries. It's a real mismatch between clocks that started together. You move them along different paths in space-time, they count different amounts of time. So a natural question follows. What kind of reality are you dealing with if how much time passed depends on the path, not just on a global clock? The same message shows up from space with much higher stakes. High-energy particles from outside the solar system slam into Earth's upper atmosphere, about 9 miles up, around 15 kilometers, and create showers of other particles. One important product is the muon, a heavier cousin of the electron. In its own rest frame, a muon lives for only a couple of millionths of a second before it decays. Even if it were moving at typical airplane speeds, that lifetime would only let it travel less than a kilometer, well under a mile, before vanishing. But detectors at Earth's surface, and even detectors deep inside mountains, see plenty of these muons, far more than you would expect if their clocks tick the same way yours do. The only way to make sense of this is to accept that in our frame, where the muons are moving at speeds close to light, their internal time is running slower. Their lifetime clock stretches out from our point of view, so they can cover tens of miles, tens of kilometers of atmosphere before they decay. When you crunch the numbers with relativity, the predicted survival rate matches the observed rate with high precision. Again, different paths, different amounts of time. So motion clearly changes how much time a clock experiences. But does gravity do the same thing, even over small height differences in your everyday world? The answer is yes, and the effect is now measured directly. Put one atomic clock on the floor and another on a shelf just 3.3 feet above it, about 1 meter. The clock higher up is sitting in slightly weaker gravity because it is a bit farther from Earth's center. General relativity says that in weaker gravity, time should run a little faster. Not metaphorically, not in a vague way, but in the actual tick rate of the clock. Modern optical lattice clocks are so precise that they can see this difference. The effect is ridiculously small, a fraction of a second over timescales longer than the age of the universe, but the instruments can pick it up to about 17 decimal places. That means that as you stand up, your head is aging faster than your feet, by a tiny amount you will never feel, but that the equations insist on. Time is not the same between your shoes and your brain. Now you have 3 hard facts. Clocks flown around Earth disagree with clocks that stayed home, in exactly the way relativity predicts. Muons moving at near light speed live longer, from our viewpoint, than their rest lifetime, and the numbers match the theory. Clocks separated by 1 meter of height in a lab tick at slightly different rates, and the difference matches the theory. This is not a loose, time sometimes seems weird. It is a precise pattern. All of these effects fit a simple idea. Different paths through space-time have different amounts of proper time between the same start and end events. Proper time is the time a clock carries with it along its world line. If a clock is moving fast or sitting in strong gravity, or both, it traces out a path that contains less proper time length than a clock that stayed slower and higher. When you say time slowed down for the fast clock, you are really saying that clock's path had less proper time length than mine. Notice what the equations do not need. They do not need a picture of time as some fluid that slows or speeds up, like syrup getting thicker. They do not need a cosmic metronome that ticks and then somehow lags for one clock and not another. They treat the situation exactly like geometry with a twist. Just as two different paths between the same 2 points in space can have different lengths, two different world lines between the same two events in spacetime can have different proper time. That is all. This leads to a brutal conclusion about the future. When a physicist writes down the world line of a clock, or of a particle, or of your spacecraft on a mission, the theory does not say, here is what happened so far and the rest will be decided later. The equations give you the clock's reading at every event along that path, past, present, and future, assuming the conditions you feed in. The whole chain of ticks is part of one solution. From the block universe point of view, that solution is a fixed object. It contains the start of the clock's life, the middle, and the end all at once. The fact that you are sitting at one particular point along your own world line, reading 2026 on your calendar, does not mean the rest of your line is undefined. It only means you do not have access to the later parts yet. The math is not waiting for the future to come into existence. It already describes those future ticks as part of the same space-time structure. So now you have a picture that is hard to dodge. Clocks do not agree, even when you build them to be identical. Their readings depend on their world lines, on their motion and their position in gravity. Those readings match a geometric theory where time is just one coordinate in a four-dimensional block, and the amount of time you live through depends on the shape of your path. That raises a bigger, sharper question. If even basic clocks fall out of sync depending on their motion and height, can you talk at all about a single clock for the whole universe? Some master time since the beginning? Or does the block picture also tear apart that last hope for a universal timeline? Is there at least one clock that everything in the universe can agree on? Some master time since the beginning that restores a single cosmic timeline? It looks like there might be, but when you push it, even that turns into more evidence that the whole history already sits there. The universe is filled with a faint microwave glow at about 2.7 degrees above absolute zero. This is the cosmic microwave background. Point an antenna anywhere in the sky and you pick it up. It's almost uniform, but not perfectly. On top of tiny random ripples, there's a clear pattern. In one direction, the radiation is a bit hotter. In the opposite direction, it's a bit colder. That pattern shows that we are moving through this sea of light. By measuring it carefully, cosmologists can work out our speed and direction relative to the background. The answer is about 230,000 miles per hour, around 370,000 kilometers per hour. There's a special frame in which this pattern disappears and the background looks the same in all directions. That frame gives you a natural rest frame for the large-scale universe and a natural way to define cosmic coordinates. In that frame, you can define a cosmic time measured by hypothetical observers who drift with the overall expansion and on average see the same thing in every direction. Cosmology ties that time to one number, the scale factor. The scale factor tells you how far apart typical galaxies are on average at each cosmic time. Early on, the scale factor is small. The universe is hot and dense. As time goes on, the scale factor grows. On large scales, galaxies separate and distances increase. Observations of distant supernovae and galaxy surveys across billions of light years show that this scale factor has been increasing, and in the last several billion years, the increase has been speeding up. When cosmologists plug the observed amounts of normal matter, and dark energy into Einstein's equations, they get a curve that tells them how the scale factor changes with cosmic time, from the early dense state to a far future diluted state. That curve is not built one step at a time. It comes out of the equations in one go. Once you specify the contents of the universe, the math gives you the entire expansion history as a single object. For each value of cosmic time, you can read off the average size of the universe and its expansion rate. It's tempting to say, this is the master clock. Time since the Big Bang in the microwave background frame is the one true time. But your telescope forces you to be more careful. Look at a galaxy 10 billion light years away. The light from that galaxy has been traveling for about 10 billion years before it reaches you. You are seeing the galaxy when the universe was maybe a third of its current age. You see younger stars and more gas. You call this looking back in time. And in a sense, that is correct. But the wording can trick you. The galaxy is not sitting out there, becoming what you see as you watch. You're now watching it update from that young state into some later states in real time. In space-time terms, that galaxy has a world line, just as you do. The light you see now left one particular event on that world line long ago in cosmic time and followed a light-like path toward you. Your world line and that light path intersect at your telescope. That intersection is the observation. You are sampling one event on the galaxy's world line. The full world line, early star formation, middle age, eventual fading, is part of the space-time structure. The fact that you only see one piece is about what lies in your past light cone, not about which parts of the galaxy are real yet. Cosmic time, defined using the background radiation, is useful. It lets you label slices of the universe where, on large scales, things look uniform. It lets you say, the universe is about 13.8 billion years old in this particular frame. But it does not cancel the relativity of simultaneity. It does not create a deep, absolute present that every observer must share. Near a black hole or a neutron star, or in a fast spacecraft, local time can be warped far away from this smooth cosmic time. Engineers planning a near light-speed mission will care about the proper time along the ship's world line, not about the age of the universe in the microwave background. So the right way to see it is this. The cosmic clock is a convenient label, not a ruling authority. It is a coordinate choice that fits the large-scale universe. It does not override the fact that different observers, moving differently, will disagree about what is now and will measure different intervals between the same events. There is no exception in the laws of physics that says, when using cosmic time, simultaneity becomes absolute again. The same space-time geometry, with local light cones and world lines, still controls which events can influence which. Look at the standard cosmological model with that in mind. The LCDM model is not a movie playing forward. It is a solution of Einstein's field equations with a few numbers plugged in. The density of normal matter, dark energy, and the overall curvature. Once you choose those, the equations define one spacetime, one block, that includes the entire expansion history. The scale factor as a function of cosmic time is part of that block. So are the light paths from distant galaxies to your detectors. When you run simulations that evolve the universe, you're just moving through different slices of a fixed space-time solution. That means even the closest thing we have to a universal clock fits inside the block universe picture. It is a way of naming slices of a four-dimensional space-time that already contains the whole past and the whole future. The Big Bang, the era of galaxy formation, today's universe, and the cold, dark future where stars have burned out all show up in the same solution once you set the parameters. The slice you currently occupy is not promoted to being more real just because you are on it. It is simply the part of the block your world line passes through right now. So the question gets sharper. If the full expansion history is already encoded in a single spacetime and cosmic time is just one coordinate on that spacetime, then what actually limits which events can affect you and which ones will never touch you, no matter how long your world line is? Right now, there are real events happening in the universe that you will never know about, not because you are too slow or not smart enough, but because the structure of spacetime forbids any signal from them ever reaching you. That sounds extreme, but it falls straight out of how relativity handles light and cause and effect. Start with one event, you at this instant watching this. Around that event, space-time splits your universe into three zones. First, there's your past light cone. That's the set of all events that could have sent out light or any signal moving at or below light speed that just barely arrives at you now. A supernova that blew up 10 years ago, 10 light years away, sits on that cone. A message your friend sent yesterday a few thousand miles away sits inside it. Second, there's your future light cone. That's the set of all events you could in principle influence if you send out a signal right now. Everything that a light pulse, a radio beam, or a spaceship traveling just under light speed could eventually reach. Third, there's the elsewhere region. Events that are outside both cones. No signal moving at or below light speed can link those events to you at this moment. So what actually enforces this split? What draws these invisible walls between can ever affect you and never will, even over infinity? The key is the finite speed of light. Light doesn't move instantly. It moves at about 186,000 miles per second, around 300,000 kilometers per second. That speed is not just a property of light, it's the maximum speed for any cause and effect signal in the universe. Take a star 100 light years away from you, about 5.9 times 10 to the 17th miles from you, around 9.5 times 10 to the 17th kilometers. If it undergoes a massive explosion right now in its own frame, that event is completely outside your current past light cone. You can't detect it. You can't be influenced by it. You can't even know it happened for 100 years. Only when the light has had time to cross those 100 light years does that event move onto the surface of one of your future light cones and then into your past light cone. Your ignorance doesn't make that explosion less real. In the block universe picture, the star, the explosion, the traveling light, and your eventual observation are all fixed events in spacetime. You just happen to be located at a point on your world line where the light hasn't arrived yet. The geometry of spacetime dictates that. The light speed limit is not a glitch, it's the rule that shapes what can talk to what. If signals are limited like that, does relativity at least keep a solid sense of before and after? Or does even that start to blur? Inside a light cone, the order of events is locked in. If event A can send a signal to event B, every observer who does the calculation correctly will agree that A comes before B. A cause cannot sit in the future light cone of its effect. If you send a radio pulse to a probe and later receive data back, every frame will agree that the transmission is earlier than the reception. That causal order is local in spacetime and absolutely fixed. Outside light cones, the story changes. Take two events so far apart and so arranged in time that no signal from one can ever reach the other at or below light speed. For them, different observers moving at different velocities can disagree about which one is earlier. One observer can say, event X happened first. Another can say, event Y happened first. A third can say, they were simultaneous. All three are using valid frames. There is no physical way to send the message from one event to the other and check which one really came first, so the laws of physics don't pick a global order. What they do enforce is the light cone structure itself, which events can be connected by signals, and which cannot. So for the universe, the priority is clear. The fundamental structure is not a single universal timeline. It's the network of light cones and world lines, the pattern of who can influence whom. The concept of earlier everywhere or later everywhere is secondary and sometimes not even well defined. Now link this back to you as a physical object. What does this light cone structure look like along your entire life, not just at one instant? As you move along your world line, each event on it has its own past and future light cones. You can think of your life as a stack of these cones, one at each moment. Move 1 second forward in your proper time, and your past light cone now contains more events, because more of the universe's history has had time to send signals that could reach you. Your future light cone also covers more potential events, because there's more time available for your signals to spread outward. From your inside view, it feels like new events are constantly entering your past light cone, and new possibilities are opening up in your future. In the block view, all of those cones and all of those events are already part of the space-time structure. You're just moving from one event on your world line to the next. The fact that your past light cone grows as you go and your future light cone shifts is a geometric fact about your track through the block, not an indication that the block is being built as you move. So far, these cones and limits still leave open the idea that given enough time, given infinite patience, you might eventually get information from anywhere, talk to anything, reach every distant galaxy. Does the universe allow that, or is there a final, non-negotiable edge to your reach? Because cosmic expansion is accelerating, there is an ultimate horizon baked into the space-time of our universe. Beyond a certain distance, galaxies are receding from us so fast, due to the stretching of space, that light emitted towards us today will never reach us. Not in 10 billion years, not in a trillion. In terms of proper distance right now, this edge is on the order of 16 billion light years away, roughly 9 times 10 to the 25th miles, around 1.5 times 10 to the 26 meters. Events beyond that horizon are forever outside your future light cone. No signal you send can catch up. No future version of you or of any civilization that descends from you will ever see those events. Again, the block universe reading is blunt. Those unreachable regions are still part of the full space-time solution. Their stars form, burn, and die. Their galaxies collide. Their black holes merge. None of it is waiting in potential. It is just permanently disconnected from your branch of the story by the geometry of the block and the rules of expansion. So you end up with a very strict picture. Light cones carve space-time into what can affect you, what you can affect, and what will remain forever out of contact. The speed of light and cosmic expansion set hard limits on your possible interactions. Inside those limits, causal order is absolute. Outside them, even the order of before and after can change depending on who is moving how. All of this fits naturally into a four-dimensional block where events simply exist. But there is something still missing. So far, nothing in this picture tells you why you feel such a strong direction from past to future, why you remember one side of your world line and not the other, why broken eggs do not reassemble and smoke does not go back into cigarettes. If the block is neutral, why does time feel like a one-way street? You see eggs break, not unbreak, smoke spread out, not jump back into the cigarette, your hard drive fill up with files, not spontaneously organize itself from random noise. Everything in daily life screams that time has a direction, but the equations you use to describe those processes work almost just as well if you run them backwards. So where does this one-way feeling actually come from? Start with entropy. Entropy is a way of counting how many microscopic arrangements fit the same big, obvious state. Think about a hot cup of coffee at 176 degrees Fahrenheit, 80 degrees Celsius, sitting in a room at 68 degrees Fahrenheit, 20 degrees Celsius. The macro description is simple. Hot coffee here, cooler air around it. But on the microscopic level, there are a ridiculous number of ways that individual molecules of air and coffee can be arranged while still matching what your eye sees. There are far fewer ways for all those molecules to line up so the coffee stays perfectly hot and separated from the room forever. So when you let the system evolve, almost all microscopic paths lead to the same outcome. The coffee cools down, the room warms up slightly, energy spreads out. The physics does not say coffee wants to cool, it says states with higher entropy, more microscopic arrangements, are overwhelmingly more likely. A tiny fraction of crazy paths would make the coffee heat itself up by stealing energy from the room, but those are so rare that you will basically never see them in the lifetime of the universe. You can see the same idea with air in a box. Put all the gas molecules in one half of the box with a divider, then remove the divider. The gas spreads out to fill the whole box. That full box state can be realized by an enormous number of microscopic configurations. The all-on-one-side state is special and rare. So the direction you call forward in time is the direction in which entropy, this count of possible microarrangements, tends to go up. Now push this away from coffee and boxes and look at the whole universe. What was the entropy story at the beginning? When you look at the cosmic microwave background, the leftover glow from the early universe, you see something surprising. A few 100,000 years after the Big Bang, matter was extremely smooth. The density only varied by about 1 part in 100,000. That means if you picked two regions of space the size of galaxy clusters, they had almost exactly the same amount of matter in them. For gravity, that smoothness is not a high entropy state. Gravity likes to make clumps. Let matter sit under its own gravity, and it collapses into clouds, then stars, then galaxies. Over billions of years, those tiny early ripples grow, and the universe becomes full of structure. Stars, planets, clusters, superclusters, and especially black holes. Black holes carry huge entropy. A universe full of scattered gas has lower gravitational entropy than a universe in which that gas has collapsed into black holes. So the early smooth universe was weirdly low entropy from gravity's point of view. Today, after billions of clumping and collapse, entropy is much higher. In the far future, when stars have burned out and most mass has fallen into black holes or been stretched by expansion, entropy will be even higher. That gives you a clear pattern. Low entropy near what you call the Big Bang end of the block, high entropy toward the far future end. Here's the key twist. The basic dynamical laws don't prefer one direction of time. Newton's laws, Einstein's equations, the core quantum rules all basically work if you replace t with minus t. A movie of two planets orbiting will still satisfy the same gravitational equations if you run it backwards. The microscopic rules don't bake in a time arrow. The arrow comes from the boundary condition. The universe is arranged to start in a low entropy state and then left to evolve. In the block universe view, that means one side of the block has low entropy, the other side has high entropy, and the interior is filled with processes where entropy increases. Your experience of this is the past, that is the future is tracking that gradient. The direction in which entropy rises is what you label forward. This is where memory and causation tie into thermodynamics, not just to abstract ideas. Every time you write a file to a 1 terabyte drive, which holds around 8 trillion bits, you're taking some physical system, the magnetic domains on the disk or the charge state in flash memory, and forcing it into one of many possible patterns that encode your data. Doing that, or erasing that data later, generates heat. It dumps energy into the environment and increases entropy. There's a minimum amount of heat per erased bit set by basic physics. The act of storing and erasing information is not free. It pushes entropy upward. Your brain is doing a similar thing when it forms a memory. Neurons change their connections, ions are pumped, chemical gradients are built and maintained. All that work produces waste heat, spreads energy, and increases entropy around you. You remember the past because the physical process that stores information about events happens as entropy rises. There is no corresponding physical mechanism that stores detailed information about future events in your brain, so your mind only carries a record in one direction of the entropy gradient. When you say A caused B, you are usually pointing to a low entropy configuration evolving into a higher entropy one in a way that can be summarized and predicted. A glass with intact structure plus normal air leads to a mess of shards plus slightly warmer air. You do not see the reverse. The notion of cause and effect rides on the fact that the universe had a low entropy boundary in what you call the past. Without that, events would still sit in spacetime, but your sense of order and prediction would not look anything like it does. Now put this back into the block picture. In a block universe, you do not need time to flow. The block is a four-dimensional object. Somewhere along one end, entropy is low. Toward the opposite end, entropy is high. Along your world line through that block, if you move in the direction where entropy increases, you call that direction into the future. The other direction, where entropy decreases, you call into the past. Nothing in this picture needs a moving present or a cosmic conveyor belt creating new slices. The arrow of time is just a large-scale pattern, the distribution of entropy across the block. Your one-way psychological experience sits on top of that pattern because your body and brain are physical systems whose operation depends on converting low-entropy resources into high-entropy waste. So here's the uncomfortable summary. The fundamental laws barely care about time's direction. The universe's low-entropy beginning plus the rule that systems tend to move toward higher entropy gives you the arrow you feel. And in a block universe, that arrow is not a force pushing you forward. It's simply the way the block is structured, with one edge tidy and the other edge extremely messy. But there is another hit waiting. If the arrow of time is just about entropy, and the core equations don't even need a built-in direction, what happens when you try to write down an equation for the entire universe at once, in quantum gravity? You start to find something even stranger. The most fundamental equation may not have time in it at all. Right now, all of this talk about block time still sounds like a big-scale thing. Galaxies, black holes, cosmic clocks. But when you zoom into the deepest level we know, quantum mechanics, you find something even extremer. At the fundamental level, the main equation might not have time in it at all. Start with ordinary quantum mechanics, the version used to describe atoms, lasers, and basic particles. In that setup, you have something called a wave function. It encodes the probabilities for different outcomes, where an electron might be, what energy level an atom might have, and so on. There's a rule that tells you how this wave function changes as time goes on. Very roughly, the energy of the system tells the wave function how to wiggle as you move from one moment to the next. You feed in the time, you get an updated wave function, and from that, you get updated probabilities. In this picture, time is not something the theory explains, it's something the theory assumes. It sits outside the system as a background parameter, like a universal clock on the wall that everything watches. Quantum mechanics, in this basic form, just takes that ticking for granted and tells you how the wave function responds. That's already awkward if you take relativity seriously, because relativity told you there's no universal time. So what happens when you try to make a quantum theory that includes gravity and that has to respect the rules of spacetime? When physicists try to make quantum gravity, they stop treating time as an outside input. Instead, they write down an equation for the entire state of the universe at once. In that equation, there's no explicit time variable playing the role of the external clock. The rule looks less like this state changes as seconds pass and more like the total energy acting on the whole universe's state has to balance in a very specific way. Technically, the total comes out to a constraint that you set to 0. You don't feed in a time and ask, what is the state now? The state just is. You describe the entire configuration of geometry and matter in one go. That's already very close to a block universe attitude. The fundamental object is not the universe at this moment, it's the universe as a whole structure. So then you have to ask, if the deepest equation doesn't have time in it, why do you feel clocks ticking and processes unfolding? Where does time come from if it's not fundamental? One important idea, suggested by Page and Wooters, is that time emerges from correlations, not from a master clock. You split the universe into two parts. One part you call the clock, the rest you call the system. You look at the full, timeless quantum state and ask, given that the clock shows this reading, what is the state of the system? Then, given that the clock shows a slightly later reading, what is the state now? Even though the global state is static, the conditional state of the system, relative to the clock, looks like it's evolving. In other words, you recover an effective time just by tracking how different parts of the universe are correlated. The global story is fixed, there's no master parameter ticking in the background, but subsystems behave as if they're evolving with respect to each other. If this picture is right, something like the block universe is built in right at the quantum level. Reality is a frozen pattern of correlations, and what you call time is how one part of that pattern indexes another. That still leaves another question hanging. Quantum mechanics also talks about superpositions and measurements. You hear that particles can be in many states at once until you measure them. If the universe is timeless at the deepest level and block-like in space-time, why do you see solid classical results instead of fuzzy superpositions everywhere? This is where decoherence comes in. Take a tiny dust grain, about 1 micrometer across, a millionth of a meter, roughly 1/100th the width of a human hair, and let it float in air. In principle, quantum mechanics says this dust grain could be in the superposition of being in several different positions at once. But in practice, air molecules and photons are constantly bouncing off it. Each collision entangles the dust grain with its environment, tying its possible positions to different states of all those outside particles. Calculations show that for a grain that size in normal air, any delicate superposition of positions is destroyed extremely fast, on timescales so short that nanoseconds look long by comparison. The environment effectively measures the grain all the time. This process is decoherence. It doesn't require a special conscious observer or a flowing external time. It just follows from the interactions already present in the full quantum state. Decoherence explains why at the scale of dust grains, cats, and people, you see well-defined positions and classical histories. The wild quantum possibilities leak into the environment and become unavailable to you. You end up tracking one stable branch of the overall pattern. You experience a world that looks classical and that seems to evolve in time, even if the underlying state is just a fixed object in a high-dimensional space. Now look at measurements themselves. Each detector click, each photon hitting a sensor, each Geiger counter spike is a specific event in spacetime. In the block view, these are just dots on the four-dimensional structure. Quantum theory gives you probabilities for which dot on your world line you will encounter. Did the detector click or not? Did the spin point up or down? From your perspective, inside the block, you talk about outcomes happening now as you move along your world line. But if you step back and draw the entire space-time picture, there's no moving spotlight scanning through the events and turning them from not yet real into real now. The different possible histories and outcomes are encoded in the structure. The probabilities come from how the wave function, or the global state, is arranged. The outcomes you actually see are the ones that lie on your particular track through that structure. So quantum theory, pushed to its limits, does not rescue the flowing present. Basic quantum mechanics starts by assuming an external time, but quantum gravity pushes that time out of the fundamental equation. Time starts looking like an internal bookkeeping device, defined by correlations between subsystems and by decoherence, not like a universal parameter that the universe obeys. Put that together with relativity, with entropy, and with light cones, and the message is consistent and blunt. At every level we test, the cleanest description is a fixed space-time structure, a block with patterns that we interpret as motion, change, and the passage of time. The theory gives you probabilities and correlations across that block, not a mechanism that creates the future as you go. And that leads you straight into the most unsettling question of all. If the future is already sitting there in the same structure as your past, if your brain activity and your choices are just parts of a four-dimensional pattern, then what exactly is left of free will? And what does it really mean to decide anything? How can you honestly say, I chose that, when your own brain starts moving toward the choice before you show up in the story? That is the kind of problem you hit when you combine neuroscience with a fixed space-time picture. In lab experiments, people are asked to do something simple, like press a button with their left or right hand whenever they feel like it. While they do that, researchers watch their brain activity with electrodes, EEG caps, or fMRI scanners. Over and over, the same thing shows up. Patterns in the brain begin to shift, ramping up toward one option, hundreds of milliseconds, sometimes seconds, before the person reports the conscious feeling of, now I've decided. The scanner can often tell, above chance, which button you are going to press before you feel the urge. That means your decision moment is not a sharp instant. It is a process stretched out along your world line. The conscious flash where you say, I just decided, is one stage in that process, not the start. In space-time terms, that whole ramp, the unconscious buildup, the conscious experience, and the muscle movement are all events along your path. You see only part of it and call that part me choosing. Now put that inside a block universe. There, your entire four-dimensional pattern is fixed. The early brain states, the ramping activity, the conscious report, the action, and the later memories of it. So you might ask, is there any room left for freedom, or are you just being dragged along by physics? First, notice something uncomfortable. The block universe does not care whether the laws are deterministic or have true randomness in them. If the universe is strictly deterministic, then once the initial conditions and the laws are specified, the entire block is fixed. Every neuron spike, every word you say, every action is determined by earlier conditions. If quantum randomness is truly fundamental, you do not escape the block, you just change its texture. The block then becomes a four-dimensional pattern that includes genuinely random events. Those events are not picked when you get there. They're just part of the structure. In both cases, probabilities in quantum mechanics are not about which parts of the block exist. They're about you, as an observer, embedded in one world line, know or do not know. When you say there's a 50% chance this atom decays in the next hour, you're talking about your uncertainty over which branch of the fixed pattern your path goes through, not about the universe flipping a coin in real time. So can you still talk about free will in a picture where the full pattern, including your decisions, is already baked in? One answer, the compatibilist answer, says yes, but you have to define freedom carefully. In this view, you are not a moving dot sliding through the block. You are the whole spread of states that make up your life, your memories, your personality traits, your habits, your values, your reactions, all laid out along your world line. Your choices are certain parts of that pattern, where certain inputs and internal states lead to certain outputs, like you quit this job, or you end that relationship, or you decide to study physics. When you say, I could have done otherwise, in strict physics terms, what you're really pointing at is this. In a slightly different block, with slightly different starting conditions for the universe, a very similar person with similar structure ends up making a different choice. You're not talking about breaking the laws of physics at the last microsecond. You're talking about how your actions depend in a stable way on your reasons, your information, and your character. Freedom then means something like this. Your actions flow from your own internal reasons and structure, not from someone forcing you at gunpoint, not from external control that bypasses your normal decision system. Inside a fixed block, that still matters. It's still true that if your beliefs or values were different, your part of the block would have a different shape. Responsibility then attaches to the full pattern of you, not to a magic power to add a different outcome at the end. At this point, you might push back and say, fine, but if the pattern is fixed, then in principle, couldn't some super intelligence predict my every move? That sounds like the final nail in the idea of meaningful choice. Here, the block picture gives you an odd sort of protection. In theory, if you had complete information about the state of the universe and unlimited computing power, you could simulate it and predict everything. But any real agent inside the block, made from matter, uses energy, and has limits, to forecast your entire life in full detail, down to every neuron and every external influence, the predictor would have to model a system as complex as you, in an environment as complex as your real surroundings. That's essentially another universe. In practice, no agent inside the block, built from finite resources, can pull that off. Psychologists and data scientists can predict some of your choices above chance, with statistics, what you're likely to buy, how long you'll watch, which posts you'll click. They find patterns, they build models, they nudge behavior, but they never reach perfect God-level prediction, and they never can, because the amount of computation and information needed grows out of reach. So even in a fixed block, the future remains opaque to any real mind living inside it, including yours. Ignorance here is not just lack of effort, it's a structural feature. So where does that leave you? In a block universe, you're not a spectator watching a pre-recorded film. You are the film, in the sense that the full four-dimensional pattern that includes your thoughts, doubts, urges, and decisions is the thing physics is talking about. The feeling of weighing options, of struggling, of making a hard call is not an illusion added on top. It's made of real physical processes in your brain, laid out along your world line. The future version of you that has already made the choice is just a later part of that same physical object. Knowing that there's a later you somewhere in the block doesn't cancel the reality of your current struggle, any more than knowing the last chapter of a book exists cancels what the characters are going through in the middle. The meaning of your choices comes from how they fit into the whole pattern, how they connect to your reasons and to the effects they have, not from some magical ability to flip fate at the final millisecond. But this raises an even harsher test for the block universe. So far, we've talked about everyday brains, fields, and particles where space-time is gently curved. What happens to this whole picture when you go to the most extreme objects we know? Black holes, where gravity stretches time and space to their limits, and horizons are defined by the entire future of space-time itself. Black holes push everything you've heard about time to the edge, and then keep going. If the block universe picture is going to break anywhere, it should break here, where gravity rips apart clocks and stretches light. But when you look closely, even black holes fit cleanly into a single, fixed space-time story. Take a simple case, a non-spinning black hole with about 10 times the sun's mass. Its event horizon, the point of no return, sits at a radius of roughly 19 miles, about 30 kilometers. If you fall in and you carry a good clock with you, you reach that horizon in just a few seconds of your own proper time once you're close. From your point of view, nothing special happens at the horizon itself. You cross it, your clock keeps ticking, your signals keep going out, at least for a while, until the gravity gradient tears you apart deeper inside. Now switch to a distant observer, far from the black hole, watching your fall with a telescope and a radio receiver. They see a different story. As you approach the horizon, the signals you send get more and more delayed. The light from your flashlight gets redder and dimmer. Your clock, seen from far away, appears to slow down. The last few signals pile up, fading and stretching, never quite showing you crossing the horizon. From that frame, you seem to freeze just outside. So, who is right? Do you cross or not? In the space-time picture, both stories are correct in their own frames, and they fit together without contradiction. Your world line crosses the horizon in finite proper time. The distant observer's slicing of space-time into now surfaces never includes an event where you are seen inside the horizon. The block does not pick one as the true story. It contains both, stitched into a single geometry where their coordinates and measurements line up. You do not have to go to black holes to see gravity attack time. Any gravitational field makes light lose energy as it climbs out. That shows up as a shift to longer wavelengths, called gravitational redshift. You can measure this in controlled experiments on Earth. Send gamma rays up and down a tower tens of yards tall, tens of meters. The rays that climb lose a tiny bit of energy and shift slightly in color. The amount matches the prediction from general relativity. Time for the lower detector runs a tiny bit slower than for the upper one, and that difference leaves a fingerprint in the light. Astronomy scales this up. Light from white dwarfs and neutron stars, objects where gravity is millions to trillions of times stronger than on Earth, also shows gravitational redshift. The spectral lines, sharp features associated with particular atoms, come out shifted compared to the same atoms in a lab. Again, the shift fits the curvature of space-time around these dense bodies. You do not see time directly. You see how the geometry changes the energy and timing of real signals, and you infer that clocks at different heights and in different fields tick at different rates. All of that is still local, though. The really deep block universe point shows up when you ask a basic question. What actually defines the event horizon of a black hole? An event horizon is not just the place where gravity feels strong or where escape velocity happens to hit the speed of light. It is defined more strictly. The event horizon is the boundary separating space-time points that can send signals to faraway observers from those that can never send signals out, no matter what they do, even if they emit light forever. To know whether a point lies inside or outside that boundary, you have to know what the entire future of space-time looks like. You need to know which light rays eventually make it to infinity and which get trapped. That is a global question. You cannot stand at one spot, take a local reading of the gravitational field, and say, this is the horizon, with certainty. You have to know the entire four-dimensional solution. In other words, the event horizon is a block universe object. Its exact shape and position depend on the full 4D structure of spacetime, not just on what's happening right now locally. You see the same block behavior when two black holes orbit and merge. Detectors like LIGO and Virgo have recorded gravitational waves from these mergers, ripples in spacetime that pass through Earth and stretch and squeeze distances by an absurdly tiny amount. In one famous case, two black holes, each about 30 times the sun's mass, spiraled together and merged in less than a second. For a brief moment, the power emitted in gravitational waves was greater than the combined light power of all the stars in the observable universe. The signal LIGO picked up was not random noise. It was a clean chirp, a rising tone with a specific frequency pattern and vamping. That pattern matches what general relativity predicts for a particular spacetime geometry describing two black holes in spiraling, merging, and settling down into one. The equations give you the entire merger history as one spacetime: the early wide orbit, the tighter final orbits, the collision, the ring down of the final black hole. The waves at Earth are just one slice through that 4D structure, one way you interact with that global story. Notice what the math is doing in all of these cases. It's not simulating space and time as they update second by second. It's solving for a space-time with certain curvature properties and energy content. Once you have that solution, before, during, and after are labels you put on different slices. The black hole forming, the horizon growing, the merger finishing all live in one geometric object. So when people say space is changing or time is getting distorted around a black hole, that's a way of talking from inside the block. In the equations, you have a single space-time that already includes the full structure. The world lines of infalling matter, the paths of light rays trying to escape, the ring of gravitational waves racing outward are all curves drawn in that space-time. Reality doesn't need to update itself as the black holes collide. The block universe, if you take it seriously, already contains the whole event from start to finish. At this point, black holes, which seemed like the most extreme challenge to any fixed picture of reality, have turned into some of the strongest evidence for it. Event horizons are defined by the full future. Gravitational redshift and time dilation fit the geometry. Gravitational waves match precise space-time solutions. The block universe reading isn't a poetic add-on. It's the most direct way to read the math. That leaves one last, massive test. If space-time is a fixed 4D object, and even black hole collisions fit into that, what about the entire expansion of the universe, from the Big Bang to the cold, dark end? Does that gigantic story also look like something already written into the block, with a future that exists in the same sense as your present? Cosmic expansion pushes you to that line because the numbers you measure today don't just describe what nearby galaxies are doing now, they lock in a whole storyline from the Big Bang to the deep future. Start with a basic observation: redshift. When you split the light of a distant galaxy into its colors and measure the lines from known atoms, those lines are shifted towards the red end of the spectrum. The farther away the galaxy, the more stretched its light is. When you measure that redshift and then measure the galaxy's distance, you get a trend called Hubble's law. A galaxy about 1 billion light-years away is typically receding from us around 14,000 miles per second, about 23,000 kilometers per second. Go out to several billion light-years, and the apparent recession speeds are a large fraction of the speed of light. Plot a lot of these galaxies, and you don't see random speeds, you see a clear pattern. Speed grows with distance in a specific way. Those points are not just random dots, they trace the expansion history of the universe. They tell you that, on average, space between galaxies is stretching, and it has been stretching for billions of years. Now, connect that to a model. The standard cosmological model is called lambda cold dark matter, or LCDM. It assumes that about 5% of the universe's energy is in ordinary matter, the stuff that makes atoms and stars. About 25% is in dark matter, which gravitates but doesn't interact with light, and around 70% is in dark energy, a smooth component that makes expansion accelerate. You plug these fractions, plus a few other parameters, into Einstein's field equations. You don't simulate 1 year at a time. You solve for a space-time that has this content. What comes out is a single continuous evolution. At very early times, the universe expands rapidly from a dense, hot state. As matter clumps and structures form, the expansion slows down a bit under gravity. At later times, dark energy dominates and the expansion speeds up again. When cosmologists fit this model to galaxy surveys, redshift data, and other measurements, they are not writing new frames as the universe goes along. They are tuning one global storyline so that all the observed slices match that one space-time solution. Dark energy adds a sharp detail, a future horizon. Because expansion is accelerating, there is a distance beyond which galaxies recede so fast that their light, even if emitted directly towards us today, will never reach us. This defines a boundary in spacetime between events that can ever affect us and events that are permanently out of reach. Today, that horizon size is on the order of tens of billions of light years. That boundary is not something the universe decides to draw later. Its shape and size are properties of the full 4D spacetime you get when you solve the equations with dark energy included. Supernova observations make this even tighter. Type 1a supernovae, exploding white dwarfs, reach peak brightness around 1 billion times that of the Sun. Because they have nearly uniform peak brightness, they act as standard candles. Measure how bright they appear and you can infer how far away they are. Measure their redshift and you know how much the universe has expanded since they went off. When astronomers plot brightness versus redshift for many of these supernovae, they see a curve that only makes sense if expansion is accelerating. Those explosions happened millions to billions of years ago in galaxies far away. Yet the pattern formed by all those ancient events lines up with a single smooth expansion history: early deceleration, later acceleration. The solution that fits the data doesn't just tell you about the past. Given the same parameters, it also tells you what happens at later and later cosmic times. The curve of the scale factor as a function of cosmic time is one object, stretching from the Big Bang all the way out to the distant future. So what does that distant future look like in this model? The answer is not comforting. In LCDM, if nothing dramatic changes, the far future is a dark, cold expansion. Galaxies outside the local group slip beyond each other's horizons. Their light never reaches us again. New stars form more and more slowly as gas is used up. Over trillions of years, the existing stars burn out. White dwarfs cool, neutron stars sit in the dark, planets freeze. On still longer timescales, even black holes evaporate by Hawking radiation. The biggest ones take an absurdly long time to disappear, on the order of a number of years with about 100 zeros after it. All of that, the fading of starlight, the isolation of galaxy groups, the slow evaporation of black holes, is part of the same space-time solution that includes you, right now, hearing about it. The equations of LCDM, once you set the parameters from today's observations, do not say here is the past and the present and will generate the future later. They give one block: early hot phase, middle structured phase, and late cold phase, all baked into the geometry. From the inside, along your world line, you only ever see a thin slice: your current cosmic time, your local environment, your past light cone. The rest is either memory, inference, or uncertainty. But the most straightforward way to read the math is that the full expansion history, Big Bang, galaxy formation, acceleration, heat death, is one object. The future is not a blank that will be written. It is the far side of that same object. So now you are pinned between two pictures. On one side, everyday experience says only the present is real. The past is gone, the future is open. On the other side, relativity, quantum ideas of time, black holes, and cosmology all push you towards a four-dimensional block where every time is equally part of the structure. Which view actually fits the physics? The one where only now is real, or the one where past, present, and future are all on the same footing? You talk and think like only the present is real, right? You say things like, that's over, and that hasn't happened yet, as if the past has been deleted and the future is just a menu of options. That gut feeling has a name: presentism. It says only the present exists, the past is gone, the future is open. It lines up with your language and your instincts, but it quietly assumes something very strong in the background: that there is a single shared now that slices the universe for everyone at once. Presentism needs that global slice. If only the present is real, you need to be able to say which events out there, in distant galaxies, on other planets, in other labs, are happening right now with you. Not just from your point of view, but in some absolute sense. Without that, the statement "only the present exists" becomes vague. The whole appeal of presentism is that it gives you a clean story. Reality is a thin layer moving from past into future, generating events as it goes. So here's the first hard question: Can physics actually give you that global, shared present that presentism needs, or is that just a story your brain tells itself? The alternative picture, eternalism, takes the block universe idea seriously. Eternalism says that past, present, and future events are all equally real parts of a four-dimensional spacetime. The universe is not three-dimensional space changing in time, it is a four-dimensional spacetime laid out as one object. Now is not a universal feature of that object. It is just a label for the slice that a particular observer is currently conscious of based on their motion and position. This is exactly how Minkowski spacetime and general relativity naturally read. The math doesn't mark certain slices as the real ones. It gives you a geometry with world lines, light cones, curvature, and so on, and then lets each observer pick coordinates. In those coordinates, you can define a time axis and a now slice, but someone moving differently will define a different time axis and a different now. Both fit the same underlying spacetime. So, which picture actually fits with relativity? Only now is real presentism, or all times are real eternalism? Relativity hits presentism head-on. With special relativity, two observers moving at a tenth the speed of light relative to each other, around 19,000 miles per second, about 30,000 kilometers per second, will disagree about which distant events are happening now. We already saw this with lightning strikes in trains. Extend that to the whole universe. Observer A makes a list of events that are simultaneous with their current moment. Observer B, moving fast relative to A, makes a different list. Those lists do not match for distant regions. If only one global present can be real, whose list wins? You might be tempted to say, there must be a hidden preferred frame, a special cosmic rest frame whose now is the true one. That would give presentism something to hold on to. But experiments have gone looking for that kind of special frame for more than a century. Ether wind tests, particle physics experiments, high-energy collisions, precision timing. They keep seeing the same thing. The laws of physics respect Lorentz symmetry, the symmetry that says no inertial frame is special. No hidden ether, no secret universal clock has ever shown up in the data. So presentism is stuck. It needs one real now, but relativity refuses to provide a unique physical way to define it. You can try to declare some frame as the true one by philosophical choice, but then you are adding invisible structure that has no effect on any measurement. You're basically stapling a ghost onto the theory. If presentism has to bolt on invisible parts, does eternalism do any better with actual experiments? Look at what we have already walked through. Atomic clocks flown on planes come back out of sync with the lap clocks by tens of billionths of a second, exactly as the space-time geometry predicts. Muons created high in the atmosphere live long enough, from our frame, to reach the ground, because their proper time along their world lines is shorter than ours. Clocks separated by 3 feet, about 1 meter, in height, tick at measurably different rates in Earth's gravity. Black hole horizons are defined by which world lines can reach infinity, using the entire future of spacetime. Gravitational wave signals fit detailed spacetime merger models. Cosmic expansion and supernova data fit a single spacetime solution from early times to a cold future. All of that hangs together cleanly if you treat spacetime as a four-dimensional object. You write down a metric, solve Einstein's equations, and you get a geometry. World lines, light cones, clocks, and fields fit into that geometry. Now slices are coordinate choices inside that geometry. Eternalism is basically just taking that picture at face value. You can try to wedge presentism back in by declaring that only one of those slices is ontologically real at any given moment, and that the others are somehow less real or not yet real. But you have to do that in a way that does not change any predictions, because the predictions already match experiment. That means your extra structure is, by design, undetectable. Physics doesn't need it, and the data do not point to it. Eternalism, by contrast, needs no such patch. It is just the straightforward reading. The block is real. This raises one last concern. If all times are equally real, Does that kill the arrow of time and flatten your experience into something featureless? Eternalism on its own says all slices exist, but it does not say they are all the same. You still have the fact that entropy is extremely low on one side of the block, near what you call the Big Bang, and much higher on the other side, toward the deep future. That's a built-in pattern. Along their world line, that means one direction in space-time is toward lower entropy and the other is toward higher entropy. You name the high entropy direction future and the low entropy direction past. So eternalism plus the entropy gradient gives you eternalism with an arrow. Everything in the block exists. Your birth, your present, your death, the death of the sun, the fade out of the last stars all sit in the structure. But there is still a clear physical sense in which one direction along your world line is special. It's the direction in which entropy grows, where memories accumulate, where broken things do not reassemble. That arrow doesn't come from a moving present. It comes from the boundary conditions of the block. Putting it all together, here's the blunt summary. Presentism matches how you talk, but it needs a single shared now that the universe doesn't provide. Eternalism matches how the equations of relativity and cosmology actually work. It accepts space-time as a four-dimensional object and treats past, present, and future as equally real parts of that object, with an internal arrow set by entropy. Every major piece of modern physics leans toward that second picture. That still leaves one more step you can't avoid. If the four-dimensional picture is not just philosophy, it should show up directly in the technology your civilization uses every day. So how much of your modern world quietly depends on treating the universe as a block of intersecting world lines, rather than as a single present moment being written on the fly? Your phone, your bank, and your satellites already bet against your gut feeling about time, and they win every day. They don't act like there's one shared universal ticking clock. They act like there's a four-dimensional space-time with intersecting world lines, and they only work because that picture is right down to meters and nanoseconds. Start with GPS because you carry it in your pocket. When your phone wants your position, it listens to signals from at least 4 GPS satellites. Each one is up at around 12,400 miles, about 20,000 kilometers, moving at around 8,700 miles per hour, about 14,000 kilometers per hour. On board each one is an atomic clock, constantly broadcasting two things. Here's where I am in orbit, and here's what my clock reads right now. Your phone receives those signals at slightly different times because the satellites are in different places. It doesn't just say, what time is it really, and then triangulate in plain 3D space. It sets up equations in spacetime. It solves for one event, the point in spacetime where all those signals could have left the satellites and arrived at your antenna, given that light speed is finite and that each satellite's clock is ticking at a rate slightly shifted by both its speed and its altitude in Earth's gravity. In other words, your phone is solving for the intersection of world lines in space-time geometry. One world line for each satellite, one for you, signals traveling along light-like paths between them. The answer is not just where you are, but where and when you are in a specific frame. If engineers ignored relativity and pretended time was universal, the timing errors would grow and your reported position would drift by miles or kilometers per day. The whole system would quietly collapse. It stays locked because the block picture is built into the code. Now look at particle physics, which sounds abstract but is brutally practical. At the Large Hadron Collider, protons are smashed together at energies of trillions of electron volts. Before anyone runs the collisions, theorists make calculations. They predict which particles should appear, at which energies, with which probabilities. The Higgs boson is the sharp example. Long before its discovery, theory said there should be a particle in roughly the 100 to 200 giga-electron volt mass range with specific decay channels and a specific bump in the data. Experimentalists then ran the collider, collected collisions for years, and plotted the results. They saw a clear excess, a bump around 125 giga-electron volts, matching the predictions. From a black universe point of view, this is not the universe writing new lines when you look. The space-time containing those collisions, that data, and those detector triggers is one fixed structure. The calculations are telling you in advance which patterns exist in that structure before you sample them. You're not forcing reality to take a path, you're uncovering a path that's already there. Focus next on satellites again, but now from the perspective of orbital mechanics. A satellite about 250 miles up, around 400 kilometers, moves at about 17,200 miles per hour, about 7.7 kilometers per second. In old Newtonian language, you'd say gravity pulls it toward Earth with a force, and its sideways speed keeps it in orbit. In general relativity language, there is no gravitational force in the usual sense. Space-time around Earth is curved. The satellite is following a natural path in that curved spacetime, a geodesic. Engineers plan orbits in that spacetime picture. They calculate how its world line bends around Earth, how its clock runs compared to clocks on the ground, how signals will travel between it and ground stations. When they fire thrusters to adjust the orbit, they're nudging its world line, changing which path through spacetime it takes. Thousands of satellites, weather satellites, communication constellations, navigation systems, space telescopes, are flying these geodesics. The fact that they go where they're supposed to go is a daily confirmation that space-time geometry is the right language. Even the basic definition of time your civilization uses assumes curved spacetime, not a flat, absolute background. The official second is defined by a specific frequency in cesium atoms. National labs around the world operate hundreds of cesium clocks and even more advanced optical clocks. These clocks sit at different altitudes, move at different speeds on Earth's surface, and experience slightly different gravitational potentials. Coordinating them into one time standard, used for everything from internet protocols to financial trades, means you cannot treat them as reading one true absolute time. You have to correct for relativity. Clocks higher up run a bit faster, clocks moving faster run a bit slower. International timekeeping is basically one huge exercise in mapping clock world lines and space-time intervals, and then defining a conventional coordinate time that glues them together. No one ever finds a special frame that deserves to be called the one real flow of time. Step back and look at the bigger picture your technology depends on. Long baseline radio telescopes spread across Earth combine signals to act like one giant dish. That only works if you know exactly how light travels in curved spacetime between distant galaxies in each antenna. Deep space missions to Jupiter, Saturn, and beyond rely on trajectory planning that includes relativistic corrections, or the probes would miss their targets by huge distances. High-frequency trading firms care about nanosecond-level timing differences between data centers, and those differences are ultimately anchored to atomic clocks linked by relativistic time standards. Every one of these systems treats where and when as one thing, not two separate layers. They treat events as points in spacetime, not as things that are being created at the edge of a moving present. They assume that if you know the geometry and the world lines, you can predict and coordinate outcomes with frightening precision. So you arrive at a blunt conclusion. The block universe view is not just a way for physicists to sound deep. It is baked into the way your civilization navigates, communicates, flies satellites, times transactions, points telescopes, and discovers particles. The four-dimensional geometry of space-time is not just a nice diagram. It is the thing your tools talk to. But if all of this is true, if technology, theory, and data all point to a fixed space-time where past and future sit side by side, then why does time feel so different from space? Why does your mind insist that there is a moving present, that the past is gone, and that the future is approaching, when nothing in the physics supports that picture? You wake up, you move through your day, and it feels like you are riding on a moving edge, a sharp present that keeps eating the future and leaving the past behind. Physics keeps saying that edge is not in the equations, so the question lands on your brain. What exactly is your mind doing to create that feeling? Start at the smallest timescales where you can still call it experience. Your nervous system is not instant. Signals from your eyes, ears, skin travel along nerves at speeds up to about 270 miles per hour, around 120 meters per second, then bounce through multiple brain regions. It takes tens to hundreds of milliseconds for raw sensory data to arrive, be combined, and become conscious. Your brain does not display each spike as it happens. It averages over a short window, maybe a tenth of a second or so, and declares, "This chunk is now." That window is huge next to the millisecond timing of individual neurons. In that tenth of a second, millions of spikes and chemical events fire inside your brain. So your present is not a razor-thin instant. It is already a small block of time, smeared out, packaged as one moment. Your awareness is always a summary of a little stretch of your world line, not a single point on it. Scale up. Over years and decades, your brain faces an impossible compression problem. Your life contains trillions of individual neural events, each located at specific milliseconds. Yet you do not remember your life as a raw timeline. You remember key scenes, transitions, and phases. Childhood, high school, that first serious job, that one disaster, that one breakthrough. You build a narrative. That narrative is not optional. It is how your brain copes with too much detail. It throws away almost all micro-level timing and keeps a coarse-grained story with causes and consequences. In a block universe, that story is one property of your four-dimensional brain trajectory. The states of your brain along your world line include both the raw microphysics and the compressed narrative over it. From the inside, that narrative feels like, "I came from back there and I am headed over there." It's your internal way of organizing a static path, as if it were a journey. Now, layer on prediction. Modern neuroscience does not see your brain as a passive camera. It sees it as a prediction engine, always slightly ahead of what hitting your senses. At any moment, parts of your brain are guessing what the next fraction of a second will look like, sound like, feel like. Sensory signals come in, those predictions are checked, errors are computed, and the internal model is updated. This loop runs constantly. Guess, compare, correct, repeat. You are hardly ever just registering the exact present input. You're using input to fix your near-future guesses. That process feels like the future approaching, because internally your model is always leaning forward, then snapping back when it's wrong. In spacetime language, your brain state at one event encodes predictions about the states at slightly later events on your world line. As you move along that world line, the parts that were predictions become memories. The flow you feel is that sliding handoff. On top of that, you never actually experience a strict instant of the outside world. Light from an object takes a finite time to reach your eyes, whether it's a lamp across the room or the sun 8 light minutes away. Electrical signals in your nerves take additional time to travel to the brain and be processed. By the time you consciously register anything, the external event is already safely inside your past light cone. You don't feel that lag because your brain edits it out. It aligns different delays so that sound, vision, and touch feel synchronized. It compensates for motion. It corrects your internal timeline so that you get one clean, unified sense of now. Even though in strict space-time terms, you're always reacting to slightly old information. What you call direct, live experience is physically always delayed. So your subjective present is built from 3 tricks. First, temporal averaging over a short window, turning a slice of time into a single moment. Second, narrative compression over long periods, turning a 4-dimensional path into a 3-dimensional story with a direction. Third, predictive modeling, always leaning into the next bit of your world line, then rewriting that section as what just happened instead of what I expected. Now, place that biological machinery back next to the physics. Relativity told you there is no universal now, only observer-dependent slices. Quantum gravity suggested that at the deepest level, there may not even be a time variable in the fundamental equation, just static correlations. Thermodynamics gave you an entropy gradient across the block, low near one side, high near the other, which shows up as the arrow you experience. Light cones and world lines carve the block into what can affect you and what cannot. Your brain sits inside that structure and runs its algorithms. It takes delayed, noisy, partial data from a thin region of spacetime along your path. It compresses that data, aligns it, uses it to update predictions, and then presents all of that to you as a smooth movie with a moving present and a one-way track. The flow is not out there in the equations. It is how your internal model represents its own changing state. This is where the pieces lock together. The simplest, unified picture that respects all of this is harsh but clear. There is a static, four-dimensional world, spacetime, containing all events: early universe, your birth, this moment, your death, the far future. Inside that block, your brain is a physical pattern along one world line. That pattern encodes memories of lower entropy regions, predictions about higher entropy regions, and a constructed present that always lags the real event slightly. That combination produces the feeling of time flowing. So your sense that the future doesn't exist yet is not a fact about the universe. It is a fact about how your nervous system works in a universe where the future region of the block is outside your current light cone and outside your current memory. The flow is a cognitive illusion, but it is not arbitrary. It is anchored in real physics, in delays, in entropy, and in the way your brain solves its information processing problem. And that brings you to the final question this whole picture forces on you. If the future already exists in the block, if your choices and their consequences are already laid out, and if the flow of time is a construction in your head, then what does it actually mean to talk about the future at all? And what are you really doing when you plan, when you worry, when you say you want to change what happens next? If the future already exists, what are you actually doing when you make a plan, change a habit, or decide not to do something stupid? Are you changing the future or just playing out a script that was there all along? In the block universe picture, there are two very different ways to look at the same thing. One is the outside perspective, the one the math suggests. From that view, the entire four-dimensional space-time is laid out at once. Your whole life is in there. Your birth, this moment, your last day. All the events on your world line are just points in one geometry. There is no moving spotlight, no line being written. The whole structure exists. Your lived perspective is totally different. From inside, you only ever know a thin band around your current moment. Behind you, there is memory, and even that is partial and distorted. Ahead of you, there is uncertainty. You can assign probabilities, you can simulate scenarios, but you do not know which one you will actually live. Both perspectives are talking about the same underlying space-time. The difference is information. The outside picture has the whole block. You, inside, have access only to the past part of your world line and guesses about the rest. That gap in information is where your sense of openness lives. You do not feel like the future is fixed because you do not know which future events are on your line. So the next question is sharp. If those future actions are already in the block, do words like responsibility and choice still mean anything? The fast answer is yes, but not for the reasons presentism suggests. In a block universe, your future actions are there, but so are the causes of those actions. The reasons you give yourself, the evidence you consider, the people who influence you, the emotions you fight with, the values you build. All of that is also part of the block. Your decision to, say, tell the truth in a hard situation is not an isolated dot. It's tied to thousands of prior events, conversations, punishments, rewards, books, videos, your genetic wiring, your learned habits. Responsibility connects to that full pattern. When you say, I am responsible for what I did, you are not claiming that you could have broken physics at the last second. You're saying that your action came out of your internal structure, your beliefs, your motives, your priorities, rather than being forced externally or produced by total chaos. Change that internal structure and the block changes shape. In a different possible block with different initial conditions, a different you with different beliefs makes a different call. Responsibility is about that dependence on your internal story, not about a magic ability to re-roll just a final frame. That leads straight into meaning. If the full story is already locked into space-time, does that make your life meaningless, just lines on a diagram? It feels like it should, but notice you don't apply that logic anywhere else. Think about a novel sitting closed on a shelf. The first page, the middle twist, and the ending all exist at once, printed in the same ink. The whole book is physically static. But when you read it, the story is not meaningless. Its meaning comes from the structure, how early events lead to later consequences, how characters grow or fail, how themes develop. The fact that the ending already exists does not make the journey inside the book fake. The point of the story is in those relationships. In a block universe, your life has the same kind of structure, just in physics instead of ink. Your significance is not in whether the universe is generating time for you on demand. It's in the overall pattern, how you affect other people, how you learn, when you mess up, what you fix, what you ignore. Two different blocks with similar starting conditions can have two very different you trajectories. One of them might contain you burning every bridge. Another might contain you fixing at least some of them. The fact that each whole block is fixed doesn't erase the difference between those two stories. Science itself fits right into this picture in a way that's a little unsettling. Every observation you make is an event in spacetime, a detector click, a telescope image, a satellite reading. As you add those events to your data, you refine your model of the block. You learn that expansion is accelerating. You measure the mass of the Higgs boson. You map temperature fluctuations in the microwave background. You are not changing the block by learning this. You, as a temporary pattern in the block, are building a better internal representation of the block. That feedback loop is weird. A small subsystem of the universe, humans, labs, telescopes, is modeling the larger space-time structure it belongs to. In the block view, the whole feedback loop is just more structure. The world lines of scientists, the development of theories, the testing, the failures, the revisions. The fact that the universe contains small pieces that can understand part of the universe is one of the strangest features of the block, not an argument against it. So here's the final twist that ties all of this together. The future already exists sounds like a threat only if you imagine that your value comes from an ability to inject new, unplanned reality into the world at the last microsecond. Physics gives you no evidence that such an ability exists. What it does give you is a picture where agency, planning, and caring are themselves physical patterns. Your curiosity about what happens next is part of the block. Your urge to change your habits is part of the block. The fact that you are even listening to this and thinking about whether any of it is true is part of the block. Some regions of space-time contain beings that model their own future branches, weigh outcomes, and act based on those models. That is not cheap window dressing. It is one of the most complex and rare structures the universe has produced. So when you plan, when you decide, when you say, I want tomorrow to go differently, you are not standing outside the block rewriting it. You are one of the patterns inside it that takes that information, runs through possible futures, and then moves along a particular world line based on that internal computation. The block universe does not erase that. It includes it. Your sense of caring about what happens next is a real physical process, and it changes which block is true when you look across all the ways the universe could have been. That is what it means in the strict, uncomfortable language of modern physics for the future to already exist. You are not outside the four-dimensional structure. You are one of the structure's sharpest details. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.